Let's take a look now at example number 2 to see if we can continue to try to practice this idea. Let's jump in here by taking a look at part A. So in here I have a function, sine of a bunch of stuff. Notice I should be able to almost see the composition immediately. I have an outer function of a sine. I have an inner function of an x squared. So to compute this, I would start by just recognizing I have sine of stuff. So what's the derivative of sine of stuff? Well, according to what we know about our trig function derivatives from the last section, that should have a derivative of cosine of stuff. That's my derivative. And then I look at the stuff. Is it just an x? No, it's not. So that means I'm going to have to follow up with the derivative of that inside stuff. So I'm going to have here a cosine of an x squared, then times the derivative of an x squared, which would be times a 2x. Or as I would typically write it, 2x times a cosine of x. Of course, the order there doesn't matter. I'd be perfectly happy with either. Let's take a look then here at part B to see how we might be able to work with this one. Notice here I have a sine squared of x. And the first thing that we should note here is to recall kind of what this means. Notice that if I have a sine squared, then that actually means that I have a sine of x all being raised to the second power, right? I have a sine times another sine. But sometimes viewing it in this way can be very helpful, because now I can kind of tell that, oh, I do have a composition here, just like I did back in part A. In fact, it's almost the exact same functions that are being composed, just in a different order. Here I had a sine function with an x squared plugged in, and here I have an x squared with like a sine plugged in. So when I compute the derivative, I'm going to start again with that outermost function. I have stuff squared. So how do I take the derivative of stuff squared? Well, I would start by using something like a power rule. I would do 2 times stuff to the first, and then I would say, look at the stuff. Is it just an x? No. So I'm going to follow up by taking its derivative. And so I would get a final answer here of 2 sine of x, and the derivative of sine of x is cosine of x. There we go. Now, actually, some of you might possibly be aware that this is actually a trig identity here. 2 sine x cosine x could actually be rewritten as the sine of 2x. That's not necessarily super important. Again, I wouldn't mark you off, say, on an exam if you wrote down 2 sine x cosine x. But again, being able to simplify things into their simplest forms can sometimes be really advantageous in future examples. So I just note that here. So what I'm going to ask you to do now is to see if you can try to practice some of these ideas on your own by taking a look at parts C and D. So go ahead and pause the video here and see if you can attempt to try to work through each of these examples. And then, of course, when you unpause the video, you'll see me work through the solutions. All right, so hopefully you actually did attempt to work on each of these. Here's how I would tackle part C. So I would notice here that what I have is a function e to the x with a 3x plugged into it. So my outermost function here is actually going to be e to the x, right? I have e to the stuff right now. And if I think back to my derivative rules, what's the derivative of e to the stuff? Well, if I think about derivative of e to the x, that was always just e to the x. So here, my derivative of e to the stuff is just e to the stuff. And then I look at the stuff, and is it just an x up there? No, it's a 3x. So I'm going to follow up with a derivative of that. And so what I'm going to end up with is e to the 3x times a 3, or I could just write that as 3e to the 3x. Okay, what about part D? Now, part D you could have actually tackled in a couple of different ways. You could have started by actually using a quotient rule here, and there would have been nothing wrong with that. But I'm going to go ahead and take a slightly different approach. We might notice right away that there is a way that I could possibly rewrite my function r of x. I could write it as x to the third plus 2 in a quantity raised to the negative 5th power. And now I could take its derivative fairly quickly. I could see that r prime of x, again, looks like stuff to the negative 5th power. And so I can take that derivative by using the power rule. I'm going to do negative 5 times stuff to the negative 6, and then look at the stuff. It's not just an x, so I'll follow up with its derivative. And its derivative here, of course, is going to be a rather simple one. I'm going to end up with, for that derivative, a 3x squared. So if I wanted to rewrite this completely, I could see that I could move this quantity to the negative 6th power into my denominator. And I could take my negative 5 times my 3 to get a negative 15, and x squared would stay on top. Now, if you did this using the quotient rule, you should actually be able to simplify your final answer all the way down to this. And so you should be able to see that we get the same answer regardless of our approach. But as you might recall, when we talked about the quotient rule in a previous section, we said that oftentimes if there was a way to kind of avoid the quotient rule, that could be really helpful since the quotient rule is sometimes a bit messier to work with. So hopefully you were able to get the answers to these particular questions here. If not, by all means, please take a look at what I've done here, rewatch this section of the video, or shoot me some questions. I'd be happy to help you try to understand a little bit maybe of what you might have gotten wrong. In the videos to come, we'll take a look at some questions using the chain rule that have some increasing complexity to them and actually require multiple implementations of the chain rule.